problem 3 on this practice exam, our function here is the square root of the quantity x plus 2. And let me just zoom that out just a bit. Okay. So we're asked to do a bunch of things with this function. And the first one is to determine whether it's one-to-one. Now, there are several different ways that we can decide that something is one-to-one. One of them is to sketch a graph and to show that it's passing the horizontal line test. If we're going to show that it's one-to-one algebraically, then the way that we would do that to show that something is one-to-one, what that means is that if I have two places, well, rather it means I can't have two x values that have the same y value. So one of the ways algebraically that we can show that something's one-to-one is to assume that f of a is equal to f of b, and then do some work to show that a has to equal b. Meaning we didn't really have two different x values where the y value is the same. If we think we have 2 points where the y value is the same, it was actually the same point. And that's what we're going to do here. So f of a equals f of b would look like the square root of a plus 2 is equal to the square root of b plus 2. And then I'm going to work through both sides and get to a place where a is equal to b. So I can square both sides of this. So a plus 2 has to be equal to b plus 2. And then I can subtract 2 from both sides and get the a is equal to b. That's one way that I can show that this is one-to-one. We can also think about what this graph looks like. And if I were to get a graph going here, I know this is shifted over to sort of start at -2. And this thing certainly passes the horizontal line test, right? No matter where I draw that horizontal line, it's only going to cross the curve exactly once. The algebra part is definitely the most rigorous way to show that it's one-to-one. Yeah. It would. So if we take a look at the way that this particular question is phrased, really the key here is to explain your reasoning. So mathematically, that means you have a choice. You can write words to explain your reasoning, or you can show math to explain your reasoning, right? But if you were to draw the picture and then explain in words that for every horizontal line that we draw, it would only pass through exactly once. Yeah.
Why do you use the horizontal line test here instead of the vertical?
So to show, it's the difference between showing that something is a function and showing that something is one-to-one. So if I were having to show that it's a function, then to be a function, that means that for every x value, there's only one y value. But one-to-one is kind of the reverse of that, that for every y value, there's only one x value. Yeah. Next part of the question is asking us about the domain. And there are only 3 things that ever go wrong with domain, and we only have to worry about 2 of them in 16A. I can't divide by 0. I can't take the square root of a negative. So when I look at this in terms of domain, it's really just telling me that x plus 2 must be greater than or equal to 0. different ways that we can write that. But I can say that x is greater than or equal to -2, or put that into interval notation and say that x is somewhere between -2 and positive infinity. And then the third part of this question is asking about the range. And so for the range, since we already have this lovely graph, I'm going to use the graph and say, oh, well, the range is from 0 to positive infinity. And we get to include the 0 because there is a value of x that we can plug in that makes the function equal to 0. Part D of the same question is getting at inverses, but yes, question first. So the way that we could potentially figure out the range without looking at the graph is by finding the inverse and looking at the domain of the inverse. The issue with this particular problem is that the inverse gets a little bit tricky, which is why he framed part D differently. Algebraically, to think about what's going on with the range, you can think about what's happening at the extreme values, right? So if I think about the extreme values of the domain being -2 and infinity, we can think about what's going on with the graph at each of those ends. So f of -2 is equal to 0. And if I looked at the limit as x approaches infinity, because I can't just plug it in, but if I took the limit as x approaches infinity of our function, I would get infinity. So we can get those ends of the range by doing a little bit more math. If you're really uncomfortable graphing. Cool. So this last part, which is about the inverse. So we've been asked to check that for positive values, that this function g of x is the inverse function of f of x. So we're presented with g of x is equal to x squared minus 2. Now to show that something is the inverse, we need to show that g of f of x, g of f of x is equal to x. Now I would argue that we should also show that f of g of x is equal to x. That if it's the inverse, then they should undo each other. So let's look at g of f of x. And if we take g of f of x, then we're going to plug f of x into this function g. So I would have the square root of x plus 2 squared, and then we subtract 2. Well, if I take the square root of x plus 2 and I square it, I get x plus 2 back. And then we're subtracting 2, and that equals x, and we're good. For completeness, if we check in the other direction, and we look at f of g of x, we're going to take the square root of x squared minus 2 plus 2. So inside of that square root, I don't actually need the parentheses anymore. I just put them in there to like show that we're plugging the thing in. But now if I take the -2 and I add a 2 to it, then I'm looking at the square root of x squared. Now there is a subtlety here. The square root of x squared is not equal to x. but it is equal to x if x is positive, which was stated in the problem itself. So this is equal to x because x is positive. And again, we're asked to do some different things with it. We were not explicitly asked to graph it, though we could, and that would be a reasonable ask. But I'm happy to do the whole thing without a picture. And if we're going to do this without a picture, then the first question on here is to find f of 2. Since x equals 2 is the value where sort of our two parts of this would be matching up, to determine which one to use at f of 2, I'm looking for the one that has the or equal. So that second part of the function has the or equal to, which means that's where I would plug in 2 to get the value. So I'd have 4 minus 2 and I'd get 2. That is the value for f of 2. The next part is that we're asked to find the limit as x approaches 2 of f of x. Well, because this is a piecewise function, even though I was only asked one question, I actually have to do 2. I have to check the limit as x approaches 2 from the left and the limit as x approaches 2 from the right. So on the left-hand side of 2, or the values where I'm a little bit less than 2, the rule for our function is x squared. We're taking that top piece of it. Yeah.
We do 2 or just the 2?
I have to do these two limits in order to answer this question. I can't answer this question without those two limits. So even though that's the only one we were asked, we have to know to go in and do these two separately. And that's going to happen anytime I have a piecewise function and we're looking at the limit where they match up. So on the left-hand side of 2, the rule we're going to follow is x squared. We're still going to do the same thing we do with any limit problem and like plug the number in. On the right-hand side of 2, it's going to be the bottom function, or the bottom part of the function rather, that's giving me the rule. So that's the 4 minus x piece. And when I plug in 2, I get 4 minus 2, or 2. These don't match. Which means this limit does not exist. Now, the next part of this question asks, is it continuous? And just as a reminder from the other day, there are 3 pieces to our definition of continuity, and all 3 of those have to be true. So this is not continuous because we've failed one piece of our continuity definition. So f of x is not continuous because, not continuous at x equals 2. When we talk about continuity, we're really thinking about like that definition of continuity with the 3 parts. That's our definition of continuity at a point. This function is actually continuous everywhere else. So it would be wrong to say that it was not continuous. It is continuous everywhere except at x equals 2. So this is not continuous at x equals 2 because the limit as x approaches 2 of f of x does not exist. If I needed to give a label to the type of discontinuity this is a jump discontinuity, and it is non-removable. I don't know if anybody talked through those 2 vocabulary words, but I'll just throw them out here as a just in case. It's a jump discontinuity, and it is non-removable. And for those of you that were hanging out with me on Tuesday, I choose to use H and not delta X because my delta X's start to look not a whole lot like deltas or X's after a bit. So in general, our limit definition of the derivative at a point would look like, well, actually, I'll just write it generally. So our limit definition of the derivative, and I'm using the notation of f prime, but you could also use dy dx or df dx. All of those would be appropriate notation. This is the limit as h approaches 0 of f of x plus h minus f of x all over h. Now that's generically for any old x value. That's how I would find the slope of the tangent line. If you're given a problem on the test where you have a particular point, you might as well use it. It generally makes the algebra easier. And because we've been given a point, I'm going to say that our slope of the tangent line when x equals 3 is going to look like the limit as h approaches 0 of f of 3 plus h minus f of 3 all over h. And by plugging in the 3 from the beginning, the algebra gets easier. So this notation of having the 3 plus h in parentheses, visually that can look like multiplication. It is not. This notation-wise is saying that wherever you see x in the original function, we're going to replace that with 3 plus h. Since our original function here is x squared minus 5, that f of 3 plus h term turns into 3 plus h squared minus 5 because I'm replacing the x with 3 plus h. Now, when we subtract f of 3, I already know what f of 3 is because we were told that the point was 3, 4, which means that that 4 is f of 3. Whole thing is divided by h, and then we work out some algebra on the top. Since we have some stuff squared, we're going to have to actually multiply that out. The negative 5 minus 4 is definitely going to give us a negative 9. I don't know how quickly or slowly it's multiplied out. Yeah. So visually, this looks like it is saying f times something. But what the notation is saying is essentially, what's the y value? When x is equal to 3. That's what that notation of f with the 3 in parentheses means. So it isn't so much that the f's have canceled out. I'm replacing f of x with its value. Like I've replaced f of 3 with the value of 4. And I've replaced f of 3 plus h with what you get when you plug in 3 plus h to the function. Okay, I'm going to multiply stuff out. So I am looking at the limit as h approaches 0. If I square this out, be careful. That's not just squaring the two terms. That's 3 plus h times a whole nother 3 plus h in parentheses. So I'm going to get 9 plus 6h plus h squared. And then I've got a negative 5 and a negative 4. So putting those together, I'll have negative 9. The 9 minus 9 is going to cancel out, which is convenient. There are a couple of different ways to finish this off, but once I've canceled out those 9s, I'm left with 6h plus h squared all over h. And we have a choice. We can either factor an h out of the numerator or rewrite that fraction to be two separate things that are both over h. I'm going to go ahead and factor. so that I've got 6 plus h on the top times h. I've got another h there, but h over h is going to give me a 1. And my very last step, I can plug in 0 for h and get a value of 6. Now, the good news is, if you know some things from a previous life, you can always check your work. So if you know how to take the derivative of x squared minus 5 using shortcuts, then you'd probably get 2x and then plug in a 3. So if you know some derivative shortcuts from a previous life, you can use them to check your work. You just can't use them to get all your points on the test. Question from over here. And I'm sorry, I didn't get your name. I'm Sarah and you are? Ella. Great. Welcome.
So why, can you explain why we plug in 0?
Oh yeah, totally. Absolutely. I'm going to draw a picture momentarily and we'll explain why we're plugging in the 0. There was another question. Same question, different question.
All the way at the end, when you cross out the 8,
Yep.
why didn't you write the 6 plus 8? Because if you cancel
It canceled those and then I plugged in the 0 for h. So that's always my sort of first goal for a limit problem is to try plugging the number in. The reason that I waited till the very end to actually plug in the 0 for h is because if I plugged it in anywhere else, I would still be at 0 over 0. So I had to get to the point where that h canceled out before I could plug in the 0 for h. Now, I think Ella's question is getting at really where is the h coming from in this formula in the first place? Maybe? Yeah, where the h is coming from in the formula in the first place. So let's do another example and I'll draw a picture and we'll talk about where that h is coming from. More questions on this before we move on. Yeah.
Are you allowed to use h in an exam? Or we can
For sure, you can use h instead of delta x. Yes, for sure. The textbook has both options. And as long as you're doing stuff that is in the textbook, you're totally fine.
H plus h squared is h.
So I factored an h out of both terms. Yeah. More questions? Yep,
So 6 is the slope of the tangent
totally.
line. Like,
Yep, that's our slope. I can't, and I don't think we were asked to actually write the equation of the tangent line, but just for fun, let's go ahead and write the equation of the tangent line since we did all this work. So if I wanted to write the equation of the tangent line, we have our point 3, 4. So I would put that into our point slope form and have y minus 4 is equal to m times x minus 3, but now we know what our slope is. So 6 times x minus 3. You could rearrange that to make it look like y equals mx plus b if you really wanted to, or we could leave it alone. If you wanted to rearrange that, that's going to look like, let's see, negative 18, and then if I add 4, so negative 14. We're going to do it generally. I'm going to sketch a graph of this, and I'm not expecting that you all know what this graph looks like. Just, I'm going to be Desmos for us today, and I'm going to sketch it. So this graph, does anyone know where the vertical asymptote is? Totally. So here's my vertical asymptote at x equals 2. Does anyone know where the horizontal asymptote is? We're going to take the limit as x approaches infinity. Where's the y value headed? 0. Because it'll be 1 divided by a huge number. So there's our horizontal asymptote at 0. And then the rest of this graph basically is going to look like this. So the whole idea of finding the slope of the tangent line is that if I have some generic point x, which means that that actual coordinate would be x comma f of x, and I take a little hop to get over here. That's why I call it h, because I took a little hop. Then the x value over here would actually be x plus h, x plus that little bit that I've moved. Which means that the coordinates here at that other point would be x plus h, comma, f of x plus h. So what we're doing when we're finding the slope of a tangent line is we're actually finding the slope of a secant line. We're going old school, finding the slope the way that we have since, I don't know what grade in school you start talking about slope. Let's pretend it was 6th grade. So you talk about slope as rise over run, or change in y over change in x. So generically, if I'm finding the slope here, I'm going to do it the same way. I'm going to look at my change in y. So f of x plus h minus f of x, because that's my change in y part, over my change in x. Well, the change in x, I went from x plus h back to x. Or if we clean up the bottom there, that's going to look like f of x plus h minus f of x all over h. Well, the whole reason that we're taking the limit as x approaches 0 is the idea behind a tangent line is we're going from finding the slope between 2 points to squeezing those 2 points together until we're actually just finding the slope at a single point. So our tangent line would look like this, where we're finding the slope at just one single point. So we take this from a secant line to a tangent line by taking the limit as h approaches 0 of all that good stuff. Now, this is just our generic formula, and then we have to apply it to a particular function. And this is our definition of the derivative. You are totally welcome to swap out the h for a delta x. Like I said, doesn't work well with my handwriting. I prefer to have an x and an h. So let's apply this to our function. I gave us a function of 1 over x minus 2. So just off to the side here, if I wanted to find f of x plus h, that means wherever there's an x, plug in x plus h. So this would turn into 1 over x plus h minus 2. And then I'm going to replace these two things in our limit formula. So I'll have the limit as h approaches 0. I'll replace f of x plus h with its formula version for this particular function, which would look like x plus h minus 2. And then we'll subtract off, plugging in our formula version of f of x, which is 1 over x minus 2. And then the whole thing will be divided by h. Once you've written this piece, then all the same rules apply in terms of a limit problem. So the first thing I would try with a limit problem is to plug in 0 for h, but we should get 0 over 0, which means we have to go do some algebra. And the type of algebra that we do depends on the problem. Well, in this case, I'm subtracting fractions. So the type of algebra that I have to do is to get a common denominator. It's going to be a little bit messy, but I think I can squeeze it in. So let's squeeze in our common denominator here. I know that this first piece, I'll have to multiply by x minus 2 over x minus 2. And our second fraction is going to need to get that other denominator, the x plus h minus 2 over x plus h minus 2. I am definitely going to need a little more space here, but I'm going to try. In my numerator, the whole point was to get this common denominator that looks like x plus h minus 2 times x minus 2. And then this whole thing was divided by h. Well, in the numerator, I've got 1 times x minus 2. Okay, I'll just write the x minus 2. And then we're subtracting this other piece. So I'm going to be careful to subtract each part of it. So I'll have a minus an x, minus an h, and minus negative 2. To save myself a little bit of space on the page and to flex about my erasable pens again, I'm going to swap out and say that instead of dividing giant division bar over h, I can actually treat that as times 1 over h. You do not have to do that. I am just saving myself space on the paper. You can leave it all over the giant h at the bottom. So now if I start cleaning stuff up, we talked about this last time, or maybe last week, but if you get 0 over 0, it means there's a factor that cancels out. So I'm really hoping that I'm going to be able to cancel that h out. So up on top, if I start simplifying this, I've got an x minus an x. Well, those are going away. I have a negative 2 minus a negative 2. Those are also going away. And the only thing I'm left with on top is that negative h, which is convenient because now the negative h over h will cancel out, leaving me with a negative 1 on the top. And it's going to be a stretch, but my h over h cancels to leave me with a 1. So I've got a negative 1 on the top, and in the denominator, now I'm ready to plug in the 0 for h. So I don't have to write limit again. When I plug in 0 for h, then I'll have x minus 2 times x minus 2. Now I'm like prepared to answer any tangent slope problem. So if you wanted to know what's the slope of the tangent line when x equals 4, bam, I plug in 4. I've got my slope. If you wanted to know what the slope of the tangent line was at x equals 0, great, I plug in 0. I've got my tangent line slope. So h in this context is the distance between my 2 points. So squeezing these 2 points together until they're touching each other, that means when they touch each other, that h value is equal to 0. So the whole idea of the limit is that we're algebraically doing the work that would squeeze these 2 points together until the distance between them was 0. If I wrote something like x minus 3 squared plus y plus 1 squared is equal to 16, just from that equation, there are really 2 things that define any circle. I need to know where the center is and what the radius is. And if we've been given the equation of a circle in this pretty nice form, then we can read off the center and the radius. So the center of this circle is going to be at whatever makes each of these pieces equal to 0. So the x value for my center would come from setting x minus 3 equal to 0. And the y value of my center would come from setting y plus 1 equal to 0. So this coordinates for the center of my circle here would be 3, -1. Now the radius, if my circle is written in this nice form of like x minus something quantity squared plus y minus something quantity squared, then that number over there on the right-hand side is the radius squared, which means here my radius would be equal to 4 because it's going to be the square root of 16. So usually what happens with circle problems is that we encounter it in not the pretty way, and then we're asked something about the center and the radius, or we're asked to graph it. And what I mean by not the pretty way is I could ask you something like, find the center and radius of, and I'm going to write this as x squared plus 6x plus y squared minus 8y is equal to 5. Well, in order to find the center and the radius of this circle, I really want to put it into our nice form, which means completing the square twice. There is really only one reason that we get circle problems in 16A, and that is as an excuse to make you complete the square, which is a skill that we're going to need in 16B. So we're just practicing it like in the context of circles. So as a refresher for completing the square, I'm going to kind of group my x terms together. I'm going to do this first one fast, and then you all can tell me if I need to slow it down. There's kind of a methodology to completing the square, but the idea is that I want x squared plus 6x plus something to give me a perfect square. Like to be something squared. And to get the what the something is, I take half of the coefficient on x. So half of 6 would give me 3, and I'd have x plus 3. And if I square the 3, I'd get 9. We did not have a 9 in the original problem. So in order to not change the problem, I am also going to add that 9 to the other side of my equal sign. Then I'm going to do the same with, and repeat that with the y values. So I'm going to look at the y part, the y squared minus 8y. And I'm going to go, okay, well, if I have y squared minus 8y, what would I add to that to make it a perfect square? I take half of the coefficient on y. So half of -8 is -4. And when you square -4, you're going to get 16. And in order to not change the problem, I'm going to add 16 to the other side. When I combine those numbers together now, 9 and 16 should be 25 plus a 5 is 30. And once it's in this nicer form, then I can just read off the center and the radius. So my center is going to be at -3, 4. And the radius, we'll just leave it messy, is going to be the square root of 30. Yeah.
Could you write out the circle or like?
Oh, yeah. For the circle or the completing the square stuff?
For the circle.
Yeah.
I just don't really remember.
Yeah. So in general, circles have a formula that looks like this, where the center is at the point HK and R is the radius. Yep. Question asked us about only one limit. The limit as x approaches 3. But I could also give you this function and then ask you to find all asymptotes. So find all the vertical asymptotes and horizontal asymptotes. Let's start. If this was the question, then vertical asymptotes are easier to identify. So I'm going to start with that. And our candidates for vertical asymptotes happen whenever the bottom is equal to 0. So if I set the denominator equal to 0 and I factor that, then +3 and -3, I said 3, wrote 1, +3 and -3 are our two candidates. So then we would go and check. So I would take the limit as x approaches 3 and see what happens with the function. And it turns out this is actually question 4. Well, the first thing that I try with any limit problem is to just plug the number in, because the answer to a limit problem is what is the y value trying to be there. So if I plug in 3, I get 0 on the top, but I also get 0 on the bottom. And 0 over 0 says do some algebra. And in this case, the algebra that I'm going to do is to factor. So in the numerator, 2x and -6, they have a 2 in common, so I can pull that out. And if I do, I'd be left with x minus 3. The denominator, I already factored before, so that's x minus 3 times x plus 3. Anytime you have 0 over 0, some factor is going to cancel out. And we just figured out which one it is. So that x minus 3 cancels out, and then I'm ready to plug in the 3 for x. So in the numerator, I've got a 2, and in the denominator, I'd have 3 plus 3, or 2 over 6, or if you like, 1/3. By the way, that means that 3 is not a vertical asymptote, because we got a number. We did not get a number divided by 0. So this tells me that x equals 3 is a whole, not a vertical asymptote. Question up front. Yes. So we're always going to look at the denominator of a fraction for candidates for vertical asymptotes. We have now eliminated one of our candidates, but we should go check the other one to see if it's a vertical asymptote. It is. So I know it's a whole because I have a factor that cancels out. Which also makes this a removable discontinuity. Let's take a look at the limit as x approaches -3 to see if that's a vertical asymptote. So if I switch this up, so we're taking the limit as x approaches -3. And really it's best to go back to the original function. When we plug in -3, by the way, this part was not part of the question that was asked on the practice test. I'm just doing extra stuff. If I plug in -3 on the top, 3 times -3 would give me -6 minus a 6. So I get -12 over 0. That's actually enough for us to know whether that's a vertical asymptote or not. That is a vertical asymptote because I got a number over 0. So x equals -3 is a vertical asymptote. Now, if we want to investigate that a little bit more and see whether we're headed to positive or negative infinity, like some of those lovely web work problems ask us to do, I'm going to take the limit as x approaches -3 from the left. And I'm just going to put in f of x for a second here. So if I approach from the left, I'm still going to get to this -12 over 0. The from the left part, I'm going to investigate to figure out whether that's a slightly positive 0 or a slightly negative 0. I always have trouble thinking about negative numbers from the left and right. So I just draw myself a quick reality check. Here's -3. So from the left on the number line, that's like -3.1. So if I were to think about plugging in something like -3.1, I just want to know, is the bottom positive or negative? Well, -3.1 squared is bigger than 9 because 3.1 is bigger than 3, which means when I plug that in, that's a slightly positive 0. And overall, this thing would be headed to negative infinity. If I look at the limit as x approaches -3 from the right, again, I'm going to end right back at -12 over 0 when I plug in the -3. But if I'm coming from the right, that's something like -2.9. Well, when I take 2.9, what was that? 2.9 squared, that's going to be a little bit less than 9 because 2.9 is a little less than 3, which makes my denominator a little bit less than 0. Because I have a negative over a negative, this would be headed to positive infinity. So if I were graphing this, which again, we're not being asked to graph it, but I'll be Desmos today. We would have a vertical asymptote at -3. As we approach from the left-hand side, we should be going down towards negative infinity. As we approach from the right-hand side, we would be going up towards positive infinity.